Okay, welcome back, everybody. It's a pleasure for me to introduce my friend and colleague, Lisa Jeffrey. Now, you all know Lisa as a very distinguished symplectic geometer, but there is a reason that Lisa is more famous than that even, but I do not have her permission right now to tell you what it is. So you'll just have to guess. So Lisa is going to talk to us about Gelfand-Cetlin systems and analogous integrable systems. Welcome, Lisa. Go ahead.
Thank you, Tony, for that introduction. To be honest, I have no idea what you're talking about. I don't know what you mean. In any case, I'm grateful to the organizers for having given me the opportunity to speak, and I am sorry that I have to do so online. I will talk about the Gelfand-Cetlin system, the work of Gilman and Sternberg. I will also talk about my joint work with Jonathan Weitzman on an analogous system. So the Gelfand-Cetlin system is a collection of functions on a cojoint orbit of UN, or in other words, a flag manifold. There are generalizations to more general Lie groups. For UN, let's stick to U, which is a Hermitian n by n matrix, so that I times U is an element of the Lie algebra of UN. The orbits of the adjoint action of the group on the space of Hermitian matrices are the collection of Hermitian matrices with fixed real eigenvalues in order. The issue with multiplying by I is so that the eigenvalues become real as opposed to pure imaginary, which is what the eigenvalues of UN are. So Gilman and Sternberg defined functions which they called Fij. So I runs from 1 to n, and j runs up to from 1 up to n minus I. And these are the eigenvalues of the square n minus I rank submatrix in the top left corner. Gilman and Sternberg showed that these functions Poisson commute, and their Hamiltonian vector fields are linearly independent almost everywhere on the flag manifold, on the tangent space, and span the tangent space to the flag manifold almost everywhere. So that sounds like a system where you have, so the number of vector fields is half the dimension of the space. So that sounds almost as if a flag manifold were a toric manifold. But in fact, flag manifolds are not toric manifolds, as we will see. In fact, it's known that the only flag manifolds that are toric manifolds are products of complex projective spaces. Proof of this combines Beilinson-Bernstein localization theorem and also an argument due to Thomson, which shows that flag varieties are what are called d-affine. In other words, they have a deformation quantization with a C-star action with respect to which they are affine. And Hemmelsoth showed that the only projective toric varieties that are d-affine are products of projective spaces. So that completes that proof. But flag manifolds are quite close to toric manifolds. In fact, there are open-dense subsets of flag manifolds which are homeomorphic to C star to the n. This was proved by Kumars Kave and also followed up by Harada and Kave 1 year later. Another proof that at least some flag manifolds are not toric manifolds goes via the Cox ring. So the Cox ring of this flag manifold is not a polynomial ring, so this manifold can't be a toric manifold. This is due to Yihu and Sean Keel, 2000. There's also an argument about Cox rings of a spherical embedding due to Gagliardi. So that's how we know that flag manifolds are not always, not in general, toric manifolds, quite rarely toric manifolds. The cohomology ring of flag manifolds is known, and also so that is toric manifold, the cohomology ring of a toric manifold due to Danilov's theorem is also known. But the argument that distinguishes flag manifolds from toric manifolds doesn't go by showing that they have cohomology rings that are different. Are there any questions to this point? By the way, please interrupt me because otherwise I will speak too quickly.
Any questions? No, any questions online? I don't think we.
Hi, Lisa. This is
Yes.
Yael. I'll just say that, I'm a little bit surprised that one has to use such heavy tools to show that only projected spaces are both toric and flag. I would expect that there would be more elementary proofs, but it's not something I know.
Okay, well, I agree with you.
That's, yeah, but maybe this is a homework for us or something.
Possibly there
It just seems just seems a little bit heavy.
Possibly there is some easier way, but certainly it isn't transparently. You write down the cohomology of a flag manifold.
No, I'm not talking about the cohomology.
I would the same as the cohomology. It does not satisfy.
I'm not talking about the cohomology. I'm just like, if you have a flag manifold, just can write down exactly what are the weights at a point, count dimensions or something more combinatorial. But I don't know, this would be just a different, something to think about later.
Yes, well, possibly there is an easier way.
It's not that I know the answer.
Any other questions?
Okay,
Other questions?
let's talk about this system of
We're good to go, Lisa.
the system of Poisson commuting functions. So they satisfy a pyramid of inequalities. So here the lambda 1 up to lambda n are the eigenvalues corresponding to the coadjoint orbit. Those are fixed. And these eigenvalues are interleaved between the eigenvalues. So f1 n minus 1 lives between lambda 1 and lambda 2. And the next one of these functions lives between lambda 2 and lambda 3, and so on. And because the n minus 2 square matrix is a submatrix of the n minus 1 square matrix, we replace this system. So the lambda 1 up to lambda n get replaced by f1 n minus 1 and f1 n minus 2 up to would be f1 1. Those become the replacements for lambda 1 up to lambda n. And then we get the same sequence of inequalities, but with the f1 n minus 1 replaced by f2 n minus 2. So these are interleaved between f1 n minus 1 and f1 n minus 2, which play the same role as the lambda 1, lambda 2 from the point of view of this submatrix. And this provides the second row of this pyramid. So the Gelfand-Cetlin pyramid you will find displayed nicely in a paper by Bullock, Eva Miranda, and Yuan-Tian Zhong. They write out the Gelfand-Cetlin pyramid. So you have n minus 1 rows like this: 1, 2, down 2, and -1. The Gelfand-Cetlin polytope is the polytope described by the above inequalities. So here the lambda1 up to lambda n are fixed. And as Jongbek Song explained to me, this polytope is not the Gelfand-Cetlin, it's not the Gelfand polytope associated to any toric manifold, because at some vertices, the number of edges is greater than the dimension of the polytope. This is also worked out in a paper of Pretslova and Smirnov, 2023. So the Gelfand-Cetlin polytope is not associated to any toric manifold. Any questions to this point?
Questions online? Any questions online? I don't think we have any questions right now.
Okay, so it's not known how to classify other examples similar to the Gelfand-Cetlin system. But one example that is known is the moduli space of equivalence classes of flat SU2 connections on an orientable compact 2 manifold. This is also known as a character variety. This is my work with Jonathan Weitzman. We rely very heavily on work by Bill Goldman. So in the language, I should have mentioned, I think everyone knows that coadjoint orbits are symplectic manifolds. The symplectic form on those is the Kirillov-Constant-Suryo symplectic form. On the character variety, the symplectic form is written in the language of flat connections by taking, so the tangent space to the space of all connections is the space of Lie algebra valued 1 forms. So just think of those as 1 forms with values in, or a matrix whose entries are 1 forms. And so A is such a matrix and B is also such a matrix. You wedge these together, that means multiply the matrices and wedge the 1 forms. Then you get a 2 form, take the trace, then you get, so A wedge B would be a matrix valued 2 form, take the trace, that's just a 2 form, and then you integrate. So that's what your symplectic form is. Goldman in 1984 showed that this space, the character variety, is smooth if the representation of the fundamental group has finite stabilizer under conjugation. In this situation, when the representation has finite stabilizer, the dimension of the space is the dimension of the group times half times the absolute value of the Euler characteristic of the surface. So Goldman showed that if the surface has no boundary, then the 2 form is a closed non-degenerate 2 form on the open set of the fundamental group of the surface represented into the group up to conjugation, consisting of points where this space is smooth. Question?
Yeah, I mean, where did on the previous page, where does the representation pi enter? I didn't see it entering.
Sorry, I glossed over the fact that the space of flat connections up to gauge equivalence is isomorphic to the space of representations of the fundamental group into the group up to conjugation. I should have explained that more clearly. So this is an omission, that pi is the fundamental group of the surface, and gauge equivalence classes of connections are isomorphic with representations of the fundamental group into the group G. G here is SU2 up to conjugation. Sorry about that. Any more questions?
No more questions.
Okay. Okay. So this is you do need the closed non-degenerate is the condition for the two form to be symplectic. So for that purpose, you need this condition of finite stabilizers. So Goldman had to use Atiyah and Bott's infinite dimensional description of this form in terms of connections, the one on the previous page, to prove that to conclude that this form was actually closed. Carchon, Yael gave the first proof using only group cohomology that the form was closed. She did not need to resort to flat connections or infinite dimensional language. So for a surface, the two form is closed only if the surface has no boundary components. Otherwise, the character variety is Poisson, and the symplectic leaves are the subsets where the holonomy of the connections around each boundary component is a constant. Those spaces are called moduli spaces of parabolic bundles. The Poisson bracket for functions on this space is described by Goldman in a paper 2 years later. So these functions are obtained from a Pence decomposition of the two manifold. So I will use alternately the language of Pence decomposition and Trinion decomposition. I think the advantage of Trinion is that it's singular, and Pence in English anyway is plural. So the number of boundary circles in a Pence decomposition is half the dimension of the moduli space. The functions can be written as theta sub j, j up to, I need to mute myself. J goes up to 3G minus 3, where the holonomy of the connection around the jth boundary circle is conjugate to a diagonal matrix with eigenvalues e to the I theta j and e to the minus I theta j. So these turn out to satisfy this collection of inequalities, which define, so there are 4 inequalities, and they define a tetrahedron inscribed in the cube of side length pi vertices, these 4 vertices. If I were giving a blackboard talk, I could easily write down the Gelfand-Cetlin pyramid. I could also easily write down the tetrahedron. I apologize for that. Anyway, those are the vertices of the tetrahedron. You can draw your own diagram. So if theta 1, theta 2, theta 3 correspond to the 3 boundary circles which form the boundary of a trinion or pair of Pence, then these variables have to satisfy these inequalities. This was worked out in my work with Jonathan Weitzman. The moment polytope for these circle actions is obtained by imposing these inequalities for every trinion in the trinion decomposition. So there are 3G minus 3 boundary circles for any Pence decomposition. Different Pence decomposition give different polyhedra, but the volume of all the polyhedra is the same, and that's equal to the symplectic volume of the character variety. So these flows Poisson commute, so we have 3G minus 3 times the dimension of the maximal torus, Poisson commuting flows. The dimension of the character variety is the Euler characteristic, absolute value of the Euler characteristic, which is 2G minus 2, times the dimension of the group. So the number of flows is half the dimension of the moduli space only if the dimension of the group is 3 times the dimension of the maximal torus. So that's SU2, SO4, or some non-compact examples, SL2R, SL2C. This is the reason why I've restricted to SU2. The flow associated to a curve C is given by the holonomy of the connection A around C is conjugate to the diagonal matrix with eigenvalues e to the I theta and e to the minus I theta. That's how this function theta is defined. Goldman's functions are always trace of the holonomy around C of the connection A. And these functions give periodic Hamiltonian flows, but the period of these flows is not constant. So these flows do not come from a Hamiltonian torus section. So Jonathan and I realized that in order to recover a Hamiltonian torus section, we had to use theta as our function instead of trace of holonomy of the connection around C. So for SU2, the Hamiltonian flow of the function theta is only well-defined when the value of the holonomy around a curve is not plus or minus the identity matrix. So these functions are well-defined on an open dense set. In other words, where these values don't appear. And this suffices to determine the symplectic volume of the moduli space and also the image of the moment map. The moment map is continuous, but not differentiable at these values. So this is another way of thinking of this, is that the way you can write down theta is cosine inverse of half the trace of the holonomy. And the function cosine inverse is not differentiable when cosine is equal to plus or minus 1. So in other words, that happens when theta is equal to 0 and pi. So those are the points where our Hamiltonian flows, the flows are not defined. The value of the function is defined, but the Hamiltonian flow is not defined. Any questions to this point?
Are there any questions online? Don't think we have any questions, Lisa.
Okay. So say some more about Poisson structures. Flag manifolds are orbits of the cojoint action on the Lie algebra. And as I mentioned, the Poisson bracket comes from the Kirillov-Kostand-Sourio form on the orbits. For character varieties, we've talked about the Poisson structure. So another way of saying this is if you have alpha, and these are the functions, I'll describe the functions used by Bill Goldman. So if alpha and beta are base loops in the surface, so we'll write these as bracket alpha, bracket beta in the fundamental group of sigma. And I'll assume that these loops intersect transversely. And I'll just write the alpha cap beta as the set of intersections. And epsilon pi alpha beta is the intersection number at a point P in that intersection. Rho from the fundamental group to G is a representation. So I'll write a function on the character variety f sub alpha. This depends on a choice of an element of the fundamental group. So this is, you evaluate your representation rho on alpha. So now you get a complex number. So Goldman writes down the Poisson bracket of these functions. He also needs to assume that if he has, so f is a class function. It's a map, which is mapped from G to the real numbers, which is invariant under conjugation. A is just a point in the group. So f of A has inner product. V is an element of the Lie algebra. So f of A will be an element of the Lie algebra. It's just obtained by differentiating your function f, where you multiply a by exponential of tv. So it turns out that for g's un, also sun, and Goldman used f of a as trace of a, it turns out that f of a is just the average of a is just half of a minus a inverse. Can be shown that this is actually an element of the Lie algebra of G. So when rho is a homeomorphism from the fundamental group to G, the Poisson bracket is defined. This is how Goldman wrote the Poisson bracket in terms of these functions. So summing over the intersection points of alpha and beta, and you have the inner product of f of rho of alpha, big F of rho alpha, and big G of rho of beta. So we had a very explicit description of the Poisson bracket. Any questions to this point? One thing you can see.
Would anybody like to ask Lisa a question? Anyone online?
One thing you can see.
I don't think we have any questions right now.
One thing you
just broke up. Would you mind repeating that? You just broke up.
One thing you can see from this is that if alpha and beta do not intersect, then the functions f sub alpha and g sub beta Poisson commute. So the Hamiltonian flows corresponding to disjoint loops are actually commuting flows. That's quite clear from this description of the Poisson bracket. Okay, so finally I will get to the quantization. Gilliman and Sternberg quantized the quantized flag manifolds using a real polarization by selecting integer values of their functions Fij. So this is.
Excuse me, Lisa.
Or Sommerfeld. Yes.
I have a question.
Yes.
Could you just
yes.
Say a couple of words about quantization by way of background before you get into it?
Okay. Geometric quantization is a procedure that replaces a symplectic manifold by a vector space, which would be thought of as the space of wave functions. So one typical way of thinking of this, the way coming from quantum mechanics, would be to take the phase space, which is R2, one coordinate is position and the other coordinate is momentum, and then the quantization is just the square integrable functions of position. Or equivalently, the square integrable functions of momentum. So functions of half the variables. Heisenberg uncertainty principle tells you that you don't want functions that depend on both sets of variables. So that is really what is called a real polarization. Typically means choosing a Lagrangian foliation of your symplectic manifold. So the way worked out by Sniatitsky to quantize a real polarization is what are called Bohr-Sommerfeld points. Those are points where the moment map takes an integer value. Sniatitsky's paper is around 1980. Another way of quantizing is what is called Kähler quantization, and that involves equipping your symplectic manifold with a complex structure. So you have a Kähler manifold, and then taking what is called a pre-quantum line bundle, which is a line bundle whose with a connection whose curvature is the symplectic form. And then your vector space, your quantizing vector space, is the space of holomorphic sections of the line bundle. So that is quantization with respect to a complex polarization. So what both Gelfand, Sternberg, and Weitzman and I did was quantizing using a real polarization. So we were using Bohr-Sommerfeld points.
Sometimes, Lisa, I've heard you refer to the topological construction of a toric variety as quantization.
I'm not sure I was the one who referred to that.
So you don't mean that when you're talking about quantization today?
I don't mean anything to do with toric manifolds.
Okay.
Necessarily. I mean, we are saying that flag manifolds and moduli spaces of flat connections have some properties in common with toric manifolds. In particular, they have torus sections defined on actions of a half-dimensional torus on at least on an open dense set. But I am not. I was explaining that these objects are certainly not toric manifolds.
Thank you.
I should actually mention that you can distinguish moduli spaces from toric manifolds by their cohomology, because moduli spaces have some cohomology in odd degree, which certainly toric manifolds do not.
Yes.
So Gelfand and Sternberg quantized flag manifolds using this real polarization by selecting and counting the integer values of these variables. And they show that the number of such integer values is equal to the dimension of the quantization of the flag manifold using a Kähler the dimension that you get using a Kähler polarization. So for them, that count comes from Borel-Weil theorem. That they used a theorem of Hermann Weyl about restrictions of representations from UK to UK minus 1. That was how they did this count. Mark Hamilton, who was a joint student of myself and Yael Carchon, studied a quantization using a real polarization, which did not include those Bohr-Sommerfeld points, which were singular fibers in the foliation of a symplectic manifold by Lagrangian submanifolds. And both Gelfand, Sternberg, and Jonathan and I needed to include some singular Bohr-Sommerfeld fibers. This makes a difference in the quantization. The Hamiltonian flow of the Fij, getting back to flag manifolds, this is not well defined if any eigenvalues of the square matrices are equal. The reason is that the function that sends a matrix to its eigenvalues is not differentiable when any of the eigenvalues are equal. So for Jonathan and me, our quantization selected integer values of the variables theta j, provided that these variables lie within the moment polytope, and we described the moment polytope by those tetrahedron inequalities. This quantization leads to the formula for the Philinda formula. This is a known formula for the quantization of this space. These people worked it out using Kähler polarization. Bovil, Laszlo, Faltings, Kumar, Tsuchiya, Ueno, Yamada, and Sagie. They were all working with complex polarization. I emphasize that what Jonathan and I did was not a proof of the Verlinde formula, just a construction of it in terms of real polarization. My student, James Uren, wrote his PhD thesis on the subject of the toric manifolds whose Gelfand-Cetlin polytope would coincide with the moment polytope for the Hamiltonian torus sections on character varieties. Sorry, it should not be Gelfand-Cetlin polytope, but just moment polytope. And he found that in most cases, these toric varieties are actually singular. So many of these polytopes are not Delzant polytopes. He found, for example, that the polytope associated to a genus 2 surface with a pensity composition consisting of two one-hole tori that are glued together along the two boundaries, this is a square pyramid. So this has 4 edges coming from the apex of the pyramid. So it is not a simple polytope, not a Delzant polytope. The polytope associated to the genus 2 surface with the other pensity composition is actually just a tetrahedron, the one that I was talking about before. And this moment polytope is the moment polytope of CP3. For SU2, the Hamiltonian flow of the function theta is only well defined when the value of the holonomy around the curve is not plus or minus the identity. So these functions are well defined on an open dense set. This suffices to determine the symplectic volume and the image of the moment map. So we must use integer values on the boundary of the moment polytope, where the Hamiltonian flows are not necessarily well defined. And the same is true for Gelfand and Sternberg's construction. They also need to include the boundary values of the moment polytope. The Hamiltonian vector fields of these functions are undefined only when the group element is in, so this is for character varieties. These are undefined only when the group element is in more than one maximal torus. In other words, the group element corresponds to a matrix with some repeated eigenvalues. In this situation, it's impossible to define the Hamiltonian vector field. This occurs on a subset of measure 0. And this occurs when any of the matrices take value identity matrix or minus the identity matrix. Any questions to this point?
Questions? Anybody online want to ask a question? Do you have any questions?
I'll give you.
No. We're okay, Lisa. Thanks.
Okay. Okay, so Goldman instead uses the functions trace of the holonomy. These are defined everywhere. Their Hamiltonian flows are periodic, but the period is not constant. And finally, Jonathan Weitzman and Peter Crooks studied in a paper last year, studied the quantization of the cotangent bundle of UN using 2 distinct real polarizations. The quantization of the first led to the square integrable functions on UN. The quantization of the other led to the direct sum of the endomorphisms of all irreducible representations of UN. The Peter-Weil theorem identifies these 2 quantizations, so giving another instance of independence of polarization. I should finally mention a paper of Jeremy Lane, who described a generalization of Gelfand-Cetlin systems to groups other than UN and systems other than coadjoint orbits. So I'll close with some references. So these were the papers of Goldman. This is the paper of Gelfand and Sternberg. And this is the paper of Mark Hamilton that I mentioned. And my paper with Jonathan Weitzman and James Uren's thesis. So I'll stop there. Thank you.
Thank you, Lisa. Let's thank Lisa for that.